Welcome back to Chem 4300. In this video, we're going to continue Chapter 17 on the quantum mechanics of rotational motion. And now we're going to look at solutions to the Schrodinger equation for describing the rotation of linear molecules. Here's a graphic I took out of Chapter 4, where we have different types of linear molecule configurations, whether it's a diatomic or triatomic, and these are the corresponding moment of inertias that we calculate. Now, we only calculate a single value here because of the symmetry of the moment of inertia tensor, which you remember we find for linear molecules that one of the principal components, the A component, is 0, and the B and C components are equal to each other, which we assign to that value of I. Now, there's a little bit of a difference here compared to the previous classifications that the linear molecule, we have to go back and reevaluate the kinetic energy expression before we come up with our Hamiltonian expression. If you remember back in that chapter, we looked at this and we noted that because there is 0 for the IA component, there can be no rotational motion about the line of the atoms. So for diatomic, it means no rotation about the bond axis. Now, since we have IA equals 0 and omega A equal to 0, our kinetic energy expression, our general kinetic energy expression for rotation, becomes this for the linear molecule. So what I'm going to do is take the relationship between the angular momentum, the rotational angular momentum, and the angular velocity vector, which we can work out here in the principal axis system of the molecule, and I get this expression here for J squared. I can rearrange this expression to give me this expression for the kinetic energy. So this is the expression for the kinetic energy. It looks exactly like the expression for the kinetic energy for the spherical molecule, but you have to be careful here because in this linear molecule, this was derived with IA equal to 0. So we'll keep that in mind as we move on to look at the quantum version of this. So in the linear molecule then, we have the A component equals 0, B and C equal to I, and we write down the kinetic energy, putting hats on the operators, and we get the Hamiltonian operator. The energy eigenvalues for this are simply going to be this, written in terms of wave numbers, and that's not a big surprise at this point. But you can see this, again, it looks the same as what we get for a spherical molecule, but it's different in some very important ways here. So first of all, again, the spherical molecule has all three components equal, but none of them are 0. Whereas in the linear molecule, one of the components is 0, while the other two are equal. So since there cannot be any rotation about the A-axis, that means that only Kj equals 0 is allowed for the linear molecule. You cannot have Kj, regardless of the J value, you cannot have a Kj value that differs from Kj equals 0 for the linear molecule. Okay. So now let's go back and look at the energy levels with our expression here for the energy. And again, it looks very similar to the symmetric molecule, but what's noticeably different is the degeneracies, because we're not allowed to have Kj other than 0. So I'll come back to that in a second here. So in other words then, for the ground state, J equals 0, then we have a singly degenerate case. For J1, we only have a degeneracy of 3 for the 3 Mj values of -1, 0, and +1. Kj can only be 0. So you can see the degeneracies correspond to 1, 3, 5, 7. Only the Mj part is contributing to the degeneracy for the linear molecule. Now, for the wave function, turns out that the Wigner-D functions with Kj equal to 0 reduce to some multiplier times the spherical harmonic functions, which we've seen before. And for when you work this out then for the wave function for the linear molecule, it's just simply 1 over square root of 2 pi times the spherical harmonics. Okay. So here's our wave function. There's Kj, I've left out the Kj because Kj is always equal to 0 for the linear molecule. Okay, again. All right, so the only degeneracy we have is associated with the Mj. All right, so that's it for this video, and the next video we'll continue on looking at the transition selection rules for rotational motion.